Hello and welcome to the lecture number 13 of Physics 401A. Previously, we saw that a complete general solution can be obtained for the motion of a single particle which is moving in one dimension only, under the condition that the particle is moving under a conservative force field. That means the force can be derived from a scalar potential function. And then we know that in the motion of the particle, we can have an integral of motion or a constant of motion independent of time explicitly. In usual case, we identify that constant as energy of the system, and using that, we could easily solve that equation. Also, there is another way to directly solve by Newton's, force equations. Now we consider in the present case the case of motion of two particles of masses m1 and m2, which are moving only under their mutual interaction. That is very important. So in the two particle system there is no net external force or field. So the two particle system, they constitute a closed system themselves, or an isolated system to be more precise. And they are not only exchanging mass with the exterior, but they are also not exchanging energy with the exterior. Under that situation, you can just, for example, think of the Earth-Sun system. Under that situation, the question is that can we solve exactly the problem? If we just now try to analyze the problem, we consider the motion of the system can in general take place in all three dimensions. Just for the most general case, then we can say that with respect to the previous problem, we have 2 degrees of additional complexities. The first one is that the number of particles is more than 1. The second one is the dimension is now no longer is 1, but it is higher than 1, it is 3. So 2 particles in 3 dimensions. Can we do something useful or effective so that we can reduce the problem at least which can be handled or which can be managed in the known ways? That is the question. So let us try to reduce the complexity as much as possible. Now let us first write the Lagrangian of the system of two particles under mutual interaction. Of course, there should be the kinetic energy terms of every particle. That will be half m1 r1 dot square plus half m2 r2 dot square, plus there will be a potential term u, which will be a function of both r1 and r2. There will be no time dependence, because time dependence only can come, if you remember, when we are talking about external fields, right? So here I just have defined that r1 and r1 dot, they are the position velocity pair for m1, and r2 dot, they are the position velocity pair for m2 respectively. Now, to be very honest, if we just ask the question whether the problem can be reduced to a simplified version if we just have a general form of u, r1 and r2, well, the answer is I don't know, to be very honest. Now, in order to simplify the problem, one way is to specify some simplified version of u as well. Some restrictive functional form for u. And that's exactly what we are doing here. Let us now assume that the potential is a function of r1 minus r2 modulus, modulus of r1 minus r2 only. That is, the potential just depends on the relative distance between the two particles. This is also true for very popular forces like gravitational interaction, Coulomb interaction, etc. So we can write the Lagrangian as half m1 r1 dot square plus half m2 r2 dot square minus u modulus of r1 minus r2. As you can see, there is an interaction term. So in general, the Lagrangian cannot be written as L1 plus L2 form. They cannot be written. Okay. And that is also natural because this is a system of interacting particles. Okay. They can be written as a sum only when we are considering two non-interacting subparts of a system, if you remember, right? Now there is a very interesting technique, okay, trick, by which we can do something useful so that we can finally write the Lagrangian as a sum of two Lagrangians. What is that? We choose two new position coordinates, as one is capital R, which is known as the CM, center of mass, okay, and that will be defined as the sum of mi ri. Here it will be simply m1 r1 plus m2 r2 by the total mass of the system m1 plus m2. So m1 plus m2, which is the total mass of the system, in some cases I will also tell it, or designate it as capital M. Okay, and another new position coordinate that will be equal to r1 minus r2, which is also easy to understand, which is the relative distance between those two particles. We can also take the dots and we have these relations 4 from that. Okay, so if this is the position of the center of mass, okay, then this is the velocity of the center of mass. Now, really, to be very honest, sometimes the center of mass can be occupied, as we discussed in the lecture number 1 or 2, okay, that center of mass can or cannot be occupied by a real particle. This is a representative position, okay, where if the total mass of the system, so basically when m1 plus m2 goes in this side, where the total mass of the system, if situated even imaginarily, then the total mass moments of that position will be exactly equal to, or that particle basically will be exactly equal to the sum of the mass moments of all the particles. That's it. And the same thing for the momentum, that if the total mass is situated at CM position, then the momentum of the CM, okay, will be the sum of the individual momentums. That's it. Now, if we do some algebra, we can show using 4, these two relations, we can show that half capital M r dot square plus half m1 m2 by m1 plus m2 times r dot square, which is the small r dot square, will be simply equal to, now this one I have defined a new thing, okay, and we will see why this is necessary, okay. This in general we call as mu and the reduced mass of the system, okay. So you see that this is, when this is written and expanded, it simply gives, this term just simply gives half m1 plus m2 times the definition of r dot, okay, this one square plus half m1 m2, the definition of small r dot, which is r1 small r1 dot minus small r2 dot whole square. Then again expanding, you can see that the cross terms will cancel with each other and you will be just left with half m1 r1 dot square plus half m2 r2 dot square, okay, which is the sum of the kinetic energy of those two particles. Now basically we can simply replace these two terms by these two terms, okay. Then the Lagrangian can also be written as this, half capital M capital R dot square plus half mu small r dot square minus u. Now capital R modulus is nothing but, small r modulus is nothing but small r itself, scalar r. So you can see at the end of the day that in this part, okay, so in this part you don't have any small r or small r dot. In this part you don't have any capital R or capital R dot. So although the two particles were mutually interacting, their center of mass and their reduced mass, these two imaginary particles, or even center of mass can sometimes be also occupied with a real particle as well, that is also possible, okay. So and actually you can see that if the one of the mass is very large, then the center of mass basically situates practically very nearly that. Okay, so just for instance, for generality, we just say that these two representative particle, center of mass and the reduced mass, they act still like non-interacting particles. Okay, and we can write thus Lagrangian as a sum of those two Lagrangians. Okay, now why this is possible? That was only possible because of this restrictive form of potential. Okay, you can also think a bit more deep why this restrictive position finally uncouple that. Okay, you can just think and ask me, I mean discuss with me. Okay, now one can easily understand that the first term, which is the kinetic energy term, or which is the Lagrangian also for the center of mass, is nothing but the Lagrangian of a free particle. If you remember, right, only for the free particle the Lagrangian contains like just the term like half m v square. Okay, where v or r dot square is the velocity of the particle. So the center of mass moves like a free particle. So the motion of the imaginary particle having reduced mass mu can now be analyzed with respect to the center of mass without losing any generality, because the physical laws with respect to the center of mass will be exactly the same if mu is analyzed with respect to any other inertial frame. Okay, so they can easily be related by choosing Galilean transformation, suitable Galilean transformation. That's it. Hence, the motion of mu can be thought to be given to be in a given external potential u. Okay, so if you now concentrate on the Lagrangian of the reduced mass mu, you will see this is simply half mu r dot square minus ur, as if mu is now having a potential or a time independent potential. Okay, and this potential is just depending on its instantaneous position. So it looks like that it is moving under an external background field. Background means that it is almost constant, so it is not changing with time, or I mean it is constant, it is not changing with time, but it's a given field. So as you can understand that this field can be thought to be produced by anything but external to the reduced mass. Now remember, now try to understand the effective Lagrangian where the basic motion can be treated, I mean can be analyzed, can be written as simply L is equal to half mu r dot square minus ur, because this part can be dropped, okay, just by choosing a suitable Galilean transformation. So basically this is the mass of the system when the problem is reduced to one particle system, right? The problem was originally two particle system, now it has become one particle system. So that's why this mass is known as reduced mass. Okay. Some people also sometimes think that reduced mass because this mass is actually smaller than both m1 and m2. Well, that is not quite correct, but you can check. I mean, okay, this can have different reasons. Okay. Now you can see that since CM frame or the center of mass frame is inertial, the motion of the real particles m1 and m2 can also be studied with respect to the CM frame without losing any generality than the older Lagrangian. I mean, what I am saying that in general when we write the Lagrangians, in general we think that the motions are studied with respect to some inertial frame. So that inertial frame can be just translated by Galilean transformation to CM frame. Okay. Then the original motion of the motion of the original real m1 and m2 particles can also be studied with respect to the CM frame, because this is an inertial frame. So what is the best way to do that? We now redefine all the position coordinates taking the CM as origin, and we define our primed coordinates, that is known as the So we use the prime coordinates for the CM frame coordinates. Those coordinates are known as CM frame coordinates. Okay. Now, if you write that in this manner, you can simply say that the Lagrangian will simply be half m1. So in principle, it should be L prime. Okay, half m1 r1 prime dot square plus half m2 r2 prime dot square minus u r1 prime minus r2 prime modulus. Okay, so r2 prime r1 prime minus r2 prime modulus is the same as r1 minus r2, right? There is no problem. So the u will be exactly the same, but there will be these things will be different. So this is not exactly the same value, to be very honest. So the Lagrange, but there will be, so the physics, the corresponding physics will be similar. Okay. Now in this Lagrangian, which is now defined with respect to the CM frame, okay, we can now, we can say by definition the total momentum. If you remember the definition of center of mass frame, the total mass moments and the total linear momentum of all the particles with respect to the CM frame must vanish by definition. Then m1r1 dot prime, or rather m1r1 prime dot, is equal to minus m2r2 prime dot, and then you can just square them, and finally you can replace r1 square r1 prime dot square by m2 square by m1 square r2 prime dot square. And if you do that in this expression of Lagrangian, at the end of the day you will have this half r2 prime dot square times m2 square by m1 plus m2 minus u of r. Okay. Now remember, what is small r? So small r is r1 prime minus r2 prime. So small r dot is minus, r1 prime dot minus r2 prime dot. Okay. Again we have this equality due to the definition of CM frame. Then we can easily say r dot is nothing but minus m2 by m1 plus 1 r2 prime dot, and so r2 prime dot can be related to just r small r dot by the ratio minus m1 by m1 plus m2. Okay. So, and again in the same way you can write r1 prime dot will be simply equal to plus m2 r small r dot, okay, by m1 plus m2. Then the total Lagrangian will simply be half m1 by m2 whole square times r dot square times m2 plus m1 by m1 times m2 minus ur. And if you now do every calculation over here, complete the calculation, you will see this is nothing but half m1 m2 by m1 plus m2 r dot square minus ur. So with respect to that was exactly what is expected, but I just showed it rigorously. So that is exactly what is expected, that when the motion of the system the two particle system is studied with respect to the CM frame, then this just becomes the motion of the reduced mass of the system, which is a motion under an effective potential u, okay, which is a function of its which is a function of the particle's instantaneous position from the origin. That's exactly what it means, right? So not really. So just a minute. There is a catch. So this is not exactly the origin, because here the origin is CM. So this is very basically this R is from some. This R is basically the position of the, or rather, I am just saying because we know, well, still we know that there is a two particle system till now. So this potential will be a function of the the value of the relative distance between those two particles. Okay. So the whole system now has a mass which is the whole system basically gives a motion, okay, describes a motion of a representative particle whose mass is equal to mu, which is equal to m1 m2 by m1 plus m2, and the effective position vector is given by the relative distance or the relative position vector of the two particles. This is the reduction of the original two body problem under a specific type of potential which is depending on the relative distance between those two particles, okay, to a single particle problem. But remember, this problem is still not totally simplified because we still have 3 dimensions to manage. Okay. In the previous lecture, we only talked about the solution of one single particle in one dimension. So that is, there are a lot of things to simplify. Okay. Now, once RT is calculated, now by using this Lagrangian, you know that this looks like a conservative, I mean like a particle moving under a conservative potential. Okay, so you can easily see that there will be an integral of motion. There can be, I mean, we expect strongly, okay, and which should look like half mu r dots r vector dot square plus u of r, right? And using that, you can integrate properly and find r of t. Now, when small r of t is calculated, r1 prime t and r2 prime as a function of time can also be calculated just by using these two relations. Okay. Now you can ask, sir, that was all the prime coordinates. How to get back to the non-prime coordinates? Well, you just use the Galilean transformation with respect to the center of mass. So you know what R2 and R1 prime and R2 prime they are. Use the proper Galilean transformation. You will have R1 unprimed and R2 unprimed. Okay. Now the question is that, can we do further simplification to this problem? The problem is still 3D. The answer is, again, we have to assume some restriction on the form of the potential. Then yes. Okay. And that exactly we will do in the next part of the lecture. Thank you.